related to our detailed discussion. So Aaron proposed that something we have been discussing a lot about chemical reaction is this equation. So, and then in this equation, we are familiar with this part pretty well. At least we have spent the whole semester trying to build up to this point. And before we go into talk about what this equation is about, and we have to really clarify what K really means, right? So, and Asia mentioned that K has something to do with a concentration of a reaction. So to really give a detailed definition of K, I can write a hypothetical generic reaction, just saying that I have a reaction, let's say a molar coefficient of this reaction is small a, the compound represented by A, so it's something like that. And I have another molar coefficient B, and that's the compound B. So these capital letter representing the chemical, the small lowercase represents its corresponding stoichiometry of the reaction. All right. So then they will become product. Again, could be a C, and again, its stoichiometry coefficient is C, and the final another product. This can be anything more than 2 or 3, or could it be 1? So this, I'm just using this as a sort of a generalized chemical reaction. So I see as you're saying that equilibrium constant K equals to what? Has something to do with the concentration. So how? Visiting students, if you know, you can raise your hand to participate in the class discussion. In fact, we have had students, previous visitors, who actually joined the discussion, which is great. So I try to make the class more like discussion style whenever we introduce a new concept. So you're saying is, so the K?
Concentration of reactants to products. Okay,
the concentration of the product. So can someone else tell us what the equilibrium constant definition for this particular reaction would be? So Aaron, you want to go? So if you want to go, then I'll get you. I think I'm gonna. So yeah, you can. Nick.
It'd be C to the C power times D to the D little d power.
Great. So that's that's let's say C to the C power D and then the D power
over A to A and B to its coefficient.
Right? Yeah, so that's, this is just a review of something you probably learned in maybe even in high school. I don't know, at least freshman chemistry. So what we mean is that if you have a chemical reaction, up to this point, we have been talking about a reaction, whether it's happened or not. We used this term a lot. So for a given chemical reaction at a certain temperature, pressure, we have been using delta G of the reaction to predict whether it's happening. So this is not go, this is go, basically it'll happen, so on and so forth. So we did all of that. Now, what we were trying to go beyond this go and not go decision then as to how much is it going to go, right? So that's what we're going to get at. So we're getting, so it's just like our other discussion. When we start off by getting some qualitative assessment of the situation first. So we get a sense whether something is going to happen or which direction it's going to go. That's all. So we use thermodynamics to do that first. The second part is let's do something quantitative, right? So that's usually how we go through this kind of discussion steps. So this is the K. Now we start from going from, this is what we learned. We have shown this is with a temperature, constant temperature pressure, if a chemical reaction Gibbs energy can be calculated based on its sign, we can make assessment whether the reaction is going to happen or not. But today what we want to do is we want to go based on the magnitude of the delta G, we can actually tell how much the reaction is going to go and to what degree. So basically, Aaron, for some reason, he already figured out this equation. He should just not come to the class and get out of here. But I'm going to try to show him that he needs to be in the class. So I'm going to ask you one more tough question, which a lot of, I think almost 80% of PhD candidates fails on this one. So, and then I hope everybody else, when you finish this discussion, you'll know why, the answer of it. So let's just say I have this question, but I'll open to everybody else. Then I think I'll make Aaron answer because he proposed this equation already. So let's just say if I have a situation where, like when you hear someone talking about a binding constant, did you hear people like, what is the KD? Right? You heard about it. Especially in the biological system, when you say a protein bind to an antibody bind to an antigen, or a protein bind a piece of DNA, people will usually say, hey, the binding constant is very tight when the KD is small, which means nanomolar. Some people say, what is the KD? So the KD usually is a special form of this binding. The reason of it is because if you have usually D means dissociation constant. So you can say, the way I write is if a protein bind a piece of DNA, or could it be any antibody or antigen, it can be anything. So they can form a complex. Now, when you describe this equilibrium, and oftentimes people actually look at the dissociation part, and so the equilibrium constant usually is flipped. So when they describe this equilibrium, they go, this complex will become protein and DNA. So now if you actually express this equilibrium constant, they call dissociation constant, and then they obviously will be the protein concentration, DNA concentration, and the protein and DNA. So if this is immolar, that's immolar, this is all immolar, you can see in the end, you will get some kind of number, and with a unit of molar, right? So some kind of molar. So, but if this number is so small, so let's just say I'm hypothetically saying, oh, I have some protein binding that's so tight, so there's so tiny amount of protein DNA get dissociated compared with the complex, that means this binds really tight. So when you go around, you hear people say, I have a very tight binder because my protein had a KD of nanomolar. What they mean is they have 10 to the minus 9 mole, or they will say 1 nanomolar. So when they say I have a strong protein binding, DNA binding protein, I have a KD in the nanomolar range, usually means this is what they meant to say. And or when you hear people say I just isolated antibody from this patient's serum that can bind this viral, we're just talking about the flu virus, right? Why it's effective or not effective. And I didn't have the flu virus shot vaccine, so that's why I got it. But for those who get it, previous year didn't work so well. Maybe the antigen they're using is not so similar, so the antibody did not really bind the antigen so tightly. Austin?
So the smaller the degree, the higher the binding?
Yeah, the smaller dissociation constant, the higher the binding. So it's just much more, it's a convention, even though we write reaction this way, but in the biological system, we do a lot of that. Now, so one of the very favorite questions we ask PhD students is like, okay, what does this corresponding to binding energy? Because we often ask the students, because when we started to describe, for example, one of the very famous protein called P53, which is found in cancer patient. So that protein is responsible to hold on the genome, make sure the genome is not mutagenized or damaged. Now, in the cancer, what happens is the protein gets mutated a lot. Now, when the protein gets mutated, every time the mutation occurs, the binding constant drops. So sometimes for theoretical analysis, people try to get an idea, for every mutation, how much binding energy do I lose? So it's a very frequent a topic of discussion as well as drug design or diagnosis and so on and so forth. So it's used a lot, and usually a lot of PhD qualified exam topic cover that, and the students always go up say, hey, this mutant caused this much of binding energy because of this. They're going to throw up this equation right off the bat. So then they'll go, okay, I'll plug this in, 10K equals to this number, right? I'll just put that in there, 10 to the minus 9, RT, I'll figure out the energy, right? If you have another protein whose mutation occurred, the number is changing, I measured another energy and then I compare, then that's how we got how much the mutants cost, the energy. So it's all good. Renee?
This is just a side question. In general, do mutations, would they cause a disproportionate amount of binding loss? Wouldn't some mutations also cause increased binding?
That's interesting, but most of the time these are so-called loss of function mutation. So in this case, it's for most of them. But your question is twofold. There are cases of so-called gain of function mutation, but also even for loss of function mutation, depends on where they're occurring, and they cause different amount of energy loss. So people usually locate a part of the protein where the protein, if the mutation there cause a lot more energy loss, they call the hotspot of binding energy. So those are the side points. And here today we want to focus on how people talk about this kind of thing. Where are the basis of these kind of discussion, right? So the very first question goes, okay, so this question is specific for Eric, since you're the one who brought this up. So I'm going to ask you, if I tend to take this 10 to the minus 9 more into here, how do I calculate the free energy of the delta G of the binding for something that's 10 to the minus 9? Right. So for example, the most common question is
compare.
Yeah. No. If I just don't, let's just say the binding constant of this guy, right? So this KD is 10 to the minus 9 more, right? So delta G of let's call this binding equals RT natural log 10 to the minus 9 more, right? What is the natural log for more? Right, that's the problem. So the very common question is, how do you take a natural log of a molar? Most of the students go like, I don't know. Well,
why don't we do both at once and then just do the ratio?
You got the point, but actually, if someone answers that, usually will pass that students. But still, that's not the main point.
Minus, and then it's ln 10 to negative 9 over the other one, and you cancel, you don't have to deal with it.
Okay, so this hopefully this will give you some motivation to pay attention to today's class. I'm not saying that you're going to go study PhD later on, but at least you can actually explain to people with a much more rational understanding of what we mean by equilibrium constant. So let's go back to here. Equilibrium constant can be empirical, which means you could be someone never studied thermodynamics. You are just interested in protein-DNA interaction, antibody-antigen interaction. You are in the laboratory. You set up multiple reactions. And as long as you fix the temperature pressure, you can start off with any different concentration. And you measure at the end, when the reaction reaches equilibrium, what the concentration of each component is. And you're curious about how these concentrations are interdependent onto each other, which means you'll carry about, for example, if you start a lot more of A and B, eventually they're going to produce C and D. And you can just do whatever you want, and of course the end point of the A, B, C, D concentration could be different, right? Because if you have a lot of A, a tiny amount of B, and then in the end you'll still have a lot of A left, but B almost exhausted. You could have equal amount of A and B, at the end you have a certain amount of A and B again. So you would end up having very different kind of distribution of the concentration of each component depending on your starting point, right? So it'll almost give you this impression that this reaction can just be any random. It all depends on the ratio you use, or even whether you have something to begin with in the product. So let's assume that you set up this reaction in so many different ways. You collect a ton of data when the reaction stops going. You measure the concentration of each, and then you just tabulate all of them. Let's just say you use nowadays computer program, machine learning, or data simulation. You just kind of one day you're like, wow, actually, no matter what you do, this is true. And then you felt like you made a big discovery called the chemical equilibrium. That's true. So you can actually arrive at the conclusion this way, as we discussed on the other thermodynamic observation. So we have these experimental observation that can be purely using raw data to do simulation. You can arrive at this. And then you will get into this situation, because when you do this, you'll get a equilibrium constant has a unit. And of course, there is no, when you do this, you will have no bearing on this equation, because this equation has nothing to do with this. Because of that, if your mind is set to just describe chemical equilibrium by using this empirical approach, this is the kind of dilemma or you'll encounter. So so the question is, clearly this relationship is established through a different means. So this is what we want to talk about. So now, to switch the perspective from this sort of concentration focused one. Now let's say what is the concept we have talked about that might help us to relate concentration to Gibbs energy. Remember now, okay, we all of a sudden we switch our focus. We say, right now we know what something is intriguing. That is, when a chemical reaction reached equilibrium, for some, these concentration of each of the component is not going to be random. They're going to be restricted by some quantitative relationship. So that's observation. Now we want to know how this is true, and is this related to the other thing we have been talking about? Because we know when the chemical reaction is not going, this becomes true. So the question is this the reason that caused that? If true, then what was the quantitative relationship we have learned in the past that can relate the concentration of each species to the Gibbs energy?
Chemical potential.
Yeah. Okay, so Kalia, you started off, so then you will responsible to guide us through the rest of the discussion. Okay, no, good. So that means you got, so chemical potential is the link between Gibbs energy and the concentration, right? So what is the relationship? Let's start with it. So we started with a number of different styles. First, we explain a chemical potential that can be related to its pure state by this relationship. This is the molar fraction of that particular substance compared with it. So this is when we talk about something gets mixed with other thing, and due to the entropic effect, its chemical potential will be lowered by the molar fraction. So that's the first observation or first rationalization we did through thermodynamics, right? Now, we have, I hope you still recall, we have then made a practical job. We said, wait a minute, but every time we actually set up a pure reference point, it's kind of inconvenient. So we decide in one of the previous lecture that it's actually much easier if we call one of the reference point, also we can call this my reference point. The molar concentration, let's just say if I'm using A as an example. Now, except in this case, the reference point is right? This sort of gets back to what Aaron is saying. That is, when I compare the chemical potential of a particular species at different point, I can arbitrarily choose any reference point. I could choose the pure state, then I'm using molar fraction to compare with it. If I choose 1 molar solution as my starting point, my 2 molar will be above it by just 2 to 1. So you'll see this is a critical concept of data to get us out of the paradox of trying to get the molar here. So some of you may already sensed it. So now before I go forward, I want to make sure, because this one I didn't tape a video, I just wrote it on the board, and I did take a picture and I put it on one of PowerPoint lecture notes. Does this make sense? Intuitively and also mathematically, right? So we can basically set up, we did something like, this molar fraction be converted into a molar times some constant, and the other molar fraction corresponds to different molar, and the same constant times a different molar. So when we subtract it, this will cancel, that cancels. So basically what happens is we can relate any molar constant solutions chemical potential to the 1 molar by this actually divided by 1. So you already notice that if I actually express A as a molar, I'm already getting into the trouble of taking a natural log of a molar, right? I'm not really taking molar. I'm taking molar concentration divided by 1 molar, because that reference 1 molar is the 1 molar concentration I'm getting. So when I'm writing this, it's implicitly saying that every time I have 1 molar number there, I'm actually divided by 1 molar. Makes sense? So if you're kind of find this is weird, and go back to review the one of the lecture we focused on reference point of the chemical potential. So then we introduced another concept, that is when we have non-ideal situation, right? So if we have a molar concentration, when we start increasing concentration, we don't increase the chemical potential as what we expect it to be proportional to the large log of the concentration, because the molecule in the solution start to interact with each other. They don't behave as freely. So there's some sort of a canceling effect. So the effective concentration of these molecules appear to be lower than what. So I make a 3 molar solution of sugar. I expect my chemical potential to be higher than by 3 divided by 1. But then I realized I only get 2.78. So it seems to be basically a reduction proportional factor. So this is when we introduce what we call activity, which is virtually effective concentration. So in this case, let's just say when you have a non-ideal situation, your concentration, this is the activity coefficient, that's the real calculated concentration, then this would be the effective concentration or activity. So I'm just reviewing since we have discussed, because when we talk about chemical equilibrium, we end up using this a lot more. So I just want to set up this correctly. In the ideal case, in the most diluted case, you do this. You just go to the laboratory, you measure the concentration. All right, so basically this means for every of this chemical, its chemical potential, let's say for A, it could relate to its standard state of that guy. Now I'm going to, of course, this can be the concentration directly if the activity coefficient equals 1, which means it's ideal, right? So I'm just to be more generic. So now I want you to be used to, all of a sudden we jump from here to here, and then what do you mean by that? So A basically is actual molar concentration times the activity coefficient. So now I'm going to do all of this. Its reference point, that means this is the ideal solution at 1 molar plus So I actually didn't do anything new here. I just kind of reviewed what we did before. Now, everybody is still with me? Any questions so far? Okay, so what is the strategy, or what come to your head? How do we relate the concentration, or in this case, it's effective concentration, to a reaction condition, so that we know this principle we learned before will constrain the behavior of the concentration of each. So how do we actually relate these two? That is, how can we actually express this language, this principle, using chemical potential language, such that we can eventually find out why these guys' concentration are not going to be randomly distributed, but rather follow some kind of a rule here. If that question makes no sense, also let me know. Does that question itself make any sense? No? Okay.
Are you asking
To
how to
find-
relate the chemical potentials to the change?
I'm just saying that because I already know the answer, sometimes it's hard for me to really describe the situation better, so I want to be careful. But I'm also trying to say, like, I'm someone who first encountered this problem. I know the chemical reaction reached equilibrium is because the Gibbs energy is equals to 0. That's something we know. So that's the definition of the principle of a chemical reaction reached equilibrium. Now, and then that's the argument of delta G. Because remember, what we're doing right now is that we're doing something that Aaron brought up today. No, actually, it was a perfect way to start this class. He brought up something. We try to do this. Now we know something about this. For this particular reaction, we know this is true. Now, and then for this reaction, we know from the first half of this class, we know this is true. And then Asia and other people already told me that for this reaction, this is true. Now, so I'm trying to say, hey, we already learned enough about this. Assuming this is something we take from our past knowledge, how can we actually demonstrate this is the case? That is, the K has something to do with some sort of delta G. And another way of saying it is that how can we actually prove that the concentration of a chemical reaction of each species is going to be constrained by some sort of constant? And that constant probably will be eventually related to the delta G. So that's I don't like what I just said, but anyway, I'm going to need some help. I know a bunch of hands raised, so Austin first.
Calculate delta G, would it be like the sum of D and C subtracting the sum of A and B?
And is that what you want to say? And other people raise hands who, Anthony, that's what you are? Okay, good. So it looks like this is a common consensus in the audience. That is, we would like to express the delta G of the reaction with the concentration. So that tells us what's going to happen when the chemical reaction is going to happen or not, or how the concentration would alter depending on what the delta G really is. So basically that's what's going on. So if we really don't know what to do, we just kind of, you can sort of, let's just imagine this is a question in exam or some sort. You apply some knowledge, because you know the purpose here is trying to somehow relate the concentration to this thing, right? So, Talia basically suggests us to go back to look at how the concentration is related to chemical potential, which is also molar Gibbs energy. So then that gives us a chance to bring the concentration back into the discussion of the delta G. So that's something we want to do here. So let's just say, okay, let's see, for any given moment, or any random starting point where I have a reaction, so that is, I have the concentration of A is AA, which means effective concentration of A is AA. Now we don't use the, basically, That's just so that you know. That's the effective concentration. Okay? So so on, so on. I'm not going to write everything. So then you have AB, yeah, AC, AD. This basically means the concentration, the effective concentration of all the components are there, right? So they're there. Now, if this is what it is, then what is the Gibbs energy difference? So suggested by Austin, also kind of agreed by a number of others of you, then basically the reaction of these, now I'm using the delta, RG basically is representing the whole reaction to be differentiated from the Gibbs energy change of phase change in this and that, or osmotic pressure. So now we often use R rather than vaporization or this kind of, or melting. So this would be basically the Gibbs energy of the product the product, which is a bunch of C molar C and C molar of. So basically, the coefficient of the C and the per mole contribution of the C and the stoichiometry of the compound D and the per mole contribution of the of the D, subtract A per mole concentration of A Make sense? Are we on together? Because the chemical potential representing, if it's pure, it's molar Gibbs energy. If it's a non-pure mixture, it's a partial molar Gibbs energy. So, so the total molar Gibbs energy contribution, as written for that stoichiometry, you count the total mole of it. But that's a good question. And that will explain where this comes from later on. So we just keep in mind all the mystery or all the sense that makes no sense. Slowly in the discussion process, already been answered. I think with the question that I was trying to point out earlier about what you can't take the natural log of a unit of the molar is answered in this discussion when we set up reference point. Okay, here you'll see pretty soon. So what you do is you simply just put everything into what we wrote here into this long expression. So it might be a little bit crowded, but we just see this guy's starting point, reference point. So all it is doing is just take all of this and put it into each of them. So now I spread them out, I take the big bracket. So the top is base. So you basically group all of this into two separation terms. One is the reference point comparison. So this will be C, of the C compound's reference point plus D. This looks pretty hairy, but it's actually conceptually, hopefully not very complicated. So this is one thing, you combine them together. This is compare the reference points Gibbs energy change, or sometimes we call standard Gibbs energy difference of the reactant. Okay, so then there's another term here. So just to be out of the board, so I'm going to jump a little bit, but I will explain to you how this is happening. With the natural log, so this guy basically can land on here as a exponential, right? So that's basic. So this term will become RT natural log ACC. Pause. Everybody with me on that one? Yeah? So that's basically a log math. Well, I wouldn't even call it trick. So the same is so RT natural log AD exponential. Yeah. Summation, time, and natural. Because RT I'm going to save outside. So basically I do this with all of this. So this is RT natural log A. This is RT natural log AD. So now, then the next term, when these two combine together as plus, then they will become a product. So I knew I could keep right, but I'm just running, but I'm going to try to be efficient in the board, but at the same time also explain you so you don't get confused here. So basically, so I would have on the top A, C, A, always think it's not the A, it's activity, efficient concentration. Okay, we don't get lost here. So A, D, D. The reason this guy goes to the bottom because they're negative, so they get divided. Now, everybody with me on this one? Well, let's say you look puzzled. This good?
Yeah.
Good to go? Okay. All right. So can someone tell me the beginning point? Why this is a constant? Why the concentration of a chemical reaction when reach the equilibrium, the concentration is no longer freely be any number. They have to be a certain number. So I'm already reached this point. But I do need someone who tell me, oh, yeah, the reason this guy is a constant is because of I'll finish fill in the blank kind of sentence. That and that, how these two statements can come together. Diego?
Is it because now that delta G reaction is 0, you can just...
So this guy is at equilibrium.
Yeah.
Delta RG equal to 0. So this whole thing is 0. Now, so to be convenient, I can also write up this part to be this guy. Just to be simple, I can call this delta RG. When everything in the chemical reaction is in the reference point. Okay, so this is the comparison of the reference point. So I can write this. So basically, delta RG at any random point gives energy. It's related to the reference point plus RT and this term. So that's good. So that means when this guy equals to 0, that's when we reach the equilibrium. Now with this, so when delta RG equals to 0, then we reach equilibrium. That means this right side is 0, right? So or delta RG this equals minus RT natural log ACC ADD A B. So first of all, we have done a lot of experiments. When we did experiment, we empirically observed that when the chemical reaction reaches equilibrium, no matter how I start off, how much the concentration of each species could be different depending on how I start the reaction. But I always have this observation there. This is a constant. So that's how you can arrive. And you can call that an equilibrium constant. Or we can look at the chemical reaction by our familiar thermodynamic argument. That is, we can express each component chemical potential. Then we can describe a chemical reaction Gibbs energy using the chemical potential, so much so that we can see how the concentration of each chemical component affect the total chemical Gibbs energy. Now, as a result, we discovered that when you reach equilibrium, you get this phenomena where mathematically we can rigorously prove that the concentration of each component and their coefficients in exponential is related to this. And we can decide to call this guy an equilibrium constant if you wish. So this is how we can say RT natural log K. So the right-hand side is a thermodynamic approach to define equilibrium constant. Now, if you approach this way, then you can see at the very beginning of the start class, when Eric brought up this equation, and I hope from here on, you'll know next time someone says, I have a KD of so and so and so, I'm trying to calculate the binding energy. I'm worried about the unit. You should tell them, no, you don't need to worry about unit, because every time you refer a chemical potential, you compare with a reference point, and the concentration virtually basically cancel. So that's the first answer to that. And then the second, obviously, the reason they're related to each other is simply because the Gibbs energy. So that's the definition, thermodynamic definition of equilibrium constant. And this is how we use the standard Gibbs energy change to predict whether a reaction goes further, how much do they go, what is the constant. So you actually look at the change of Gibbs energy at the standard state to predict how far this reaction is going to go. Okay, so next class we'll expand the discussion a little bit more, but hopefully this will give you a starting point. Make sense, Aaron? Now you know what that. So do you have a different understanding of delta G equals RT log?
Wait, what if your unit is like molarity square?
Molarity square. All of these will be cancelled out because unit is set up. Because when you go back to here, you'll see. Yeah. Okay?
Thank you so much.
Because when you do this, they all be gone.